Good morning. Looks like we're live, and this time OBS is starting up just fine. I've been trying to update it to see if this random not starting problem that I've been having with it would go away, but it just isn't here. It's very weird. Like the first time I try to launch it, just doesn't launch, and then the second time it launches just fine, which doesn't really matter too much. Today, we're going to be continuing on with object-oriented programming features of Rust. So this is going to be chapter 17. It looks like there's 3 subchapters, and it looks like it's going to be about sort of like the object-oriented paradigms of other languages and which of those are available to us in Rust, which is pretty nice. Object-oriented was the first major paradigm that I learned when I started actual programming as opposed to just systems administration. So this will be interesting to go into, and then we'll move on to 18. 19 and then 20, where we have that create a web server from scratch project. All right, so with that, let's begin. Object-oriented programming features of Rust. Object-oriented programming, OOP, is a way of modeling programs. Objects came from Simula in the 1960s. Those objects influenced Alan Kay's programming architecture in which objects passed messages to each other. He coined the term object-oriented programming in 1967 to describe this architecture. Many competing definitions describe what OOP is. Some definitions would classify Rust as object-oriented, but other definitions would not. In this chapter, we'll explore certain characteristics that are commonly considered object-oriented and how those characteristics translate to idiomatic Rust. We'll then show you how to implement an object-oriented design pattern in Rust and discuss the trade-offs of doing so versus implementing a solution using some of Rust's strengths instead. All right. And I probably want to pause you. Don't need you up and running. There is no consensus in the programming community about what features a language must have to be considered object-oriented. Rust is influenced by many programming paradigms, including OOP, for example. We explored the features that came from functional programming in Chapter 13. Arguably, OOP languages share certain common characteristics, namely objects, encapsulation, and inheritance. Let's look at what each of those characteristics means and whether Rust supports it. Objects contain data and behavior. The book Design Patterns, Elements of Reusable Object-Oriented Software by Inomigama, Richard Helm, Ralph Johnson, and John Vicedes, colloquially referred to as the Gang of Four book, is a catalog of object-oriented design patterns. It defines OOP this way. Object-oriented programs are made up of objects. An object packages both data and the procedures that operate on that data. The procedures are typically called methods or operations. Using this definition, Rust is object-oriented. Structs and enums have data, and IMPL blocks, implement blocks, provide methods on structs and enums. Even though structs and enums with methods aren't called objects, they provide the same functionality, according to the Gang of Four's definition of objects. Good morning, stacking. Encapsulation that hides implementation details. Another aspect commonly associated with OOP is the idea of encapsulation, which means that the implementation details of an object aren't accessible to code using that object. I'm feeling better where I can actually chat today. Awesome. I'm glad you're feeling better. And I don't want to ever feel like I'm pressuring somebody into chatting. Totally optional. And if you feel like chatting, thank you so much. It's really awesome. And if you feel like just watching, also thank you so much. It's really awesome to have you here and watching. Where was I? Therefore, the only way to interact with an object is through its public API. Code using the object shouldn't be able to reach into the object's internals and change data or behavior directly. This enables the programmer to change and refactor an object's internals without needing to change the code that uses the object. Trust me, you couldn't pressure me into chatting yesterday. I was going to lurk no matter what. Well, and that's fine. I'm glad that you're feeling better. It always sucks whenever I'm feeling, anybody is feeling better. We discussed how to control encapsulation in Chapter 7. We can use the pub keyword to decide which modules, types, functions, and methods in our code should be public. And by default, everything else is private. For example, we can define a struct averaged collection that has a field containing a vector of I32 values. The struct can also have a field that contains the average of the values in a vector, meaning the average doesn't have to be computed on demand whenever anyone needs it. In other words, average collection will cache the calculated average for us. Listing 17.1 has the definition of the average collection struct. So pub struct, average collection are the list, which is a vector, and then the average. The struct is marked pub so that other code can use it, but the fields within a struct remain private. This is important in this case because we want to ensure whenever a value is added or removed from the list, the average is also updated. We do this by implementing add, remove, and average methods in a struct, as shown in listing 17.2. So we implement for it, so we have add, which is just pushing a value into the list, and then also immediately updating the average, like calling the update average. Remove pops an item off the list, then matches on that if basically there are still values in the list, then we run the update. Otherwise, the list is empty now, and we don't do anything. And then average obviously is just calculating the average. Oh no, this is returning the average. This is getting the average. And then update average is actually doing the calculation. It's iterating through the vector, it's summing that up, and then it's setting the average. The public methods add, remove, and average are the only ways to modify an instance of averaged collection. When an item is added to list using the add method or removed using the remove method, the implementations of each call the private update average method that handles updating the average field as well. We leave the list and average fields private, so there is no way for external code to add or remove items to the list field directly. Otherwise, the average field might become out of sync when the list changes. The average method returns the value in the average field, allowing external code to read the average but not modify it. Because we have encapsulated the implementation details of the struct averaged collection, we can easily change aspects, such as the data structure, in the future. For instance, we could use a hash set instead of a vec for the list field, as long as the signatures of the add, remove, and average public methods stay the same. Code using average collection would need to change. If we made list public instead, this wouldn't necessarily be the case. Hashset and vec have different methods for adding and removing items, so the external code would likely have to change if it were modifying list directly. If encapsulation is a required aspect for a language to be considered object-oriented, then Rust meets that requirement. The option to use pub or not for different parts of code enables encapsulation of implementation details. Inheritance as a type system and as code sharing. Inheritance is a mechanism whereby an object can inherit from another object's definition, thus gaining the parent object's data and behavior without you having to define them again. He went back to watch the VODs yesterday because the options chapter is a little poorly written. Yeah, I've been working on a book for a while. It's really interesting. Reading everything out loud slows everything down, but I feel that by doing that, I don't actually I have more idea about how Rust is working. And it's like an idea that I've been forming about education, which is rushing through the book and just reading it quietly. We might trick ourselves into thinking we're getting it. You have to read out loud also. Yeah, I mean, and the thing is, I don't like to read out loud when I'm by myself, but when I'm streaming, I feel like it feels different. Like it doesn't feel, well, I guess because I have an audience, but even though you're not in the room with me here, it just feels more normal and more okay. If a language must have inheritance to be an object-oriented language, then Rust is not one. There is no way to define a struct that inherits the parent struct's fields and method implementations. However, if you're used to having inheritance in your programming toolbox, you can use other solutions in Rust, depending on your reason for reaching for inheritance in the first place. You choose inheritance for two main reasons. One is for reuse of code. You can implement particular behavior for one type, and inheritance enables you to reuse that implementation for a different type. You can share Rust code using default trait method implementations instead, which you saw in listing 1014, when we added a default implementation of the summarize method on the summary trait. Any type implementing the summary trait would have the summarize method available on it without any further code. This is similar to a parent class having an implementation of a method and an inheriting child class always also having implementation of the method. We can also override the default implementation of the summarize method when we implement the summary trait, which is similar to a child class overriding the implementation of a method inherited from a parent class. The other reason to use inheritance relates to the type system, to enable a child type to be used in the same place as a parent type. This is also called polymorphism, which means that you can substitute multiple objects for each other at runtime if they share certain characteristics. So polymorphism. To many people, polymorphism is synonymous with inheritance, but it's actually a more general concept that refers to code that can work with data of multiple types. For inheritance, those types are generally subclasses. Rust instead uses generics to abstract over different possible types and trait bounds to impose constraints on what those types must provide. This is sometimes called bounded parametric polymorphism. Inheritance has recently fallen out of favor as a programming design solution in many programming languages because it's often at risk of sharing more code than necessary. Subclasses shouldn't always share all characteristics of their parent class, but will do so with inheritance. This can make a program's design less flexible. It also introduces the possibility of calling methods on subclasses that don't make sense or that cause errors because the methods don't apply to the subclass. In addition, some languages will only allow a subclass to inherit from one class, further restricting the flexibility of a program's design. For these reasons, Rust takes a different approach, using trait objects instead of inheritance. Let's look at how trait objects enable polymorphism in Rust. Hopefully by the end of this week, you can put this 5-month learning into good use. I'm hoping so. What's really been fun is like going into work, and I have there's a couple people in town that I chat with regularly who are also Rustaceans. Plus there's there's a Rust meetup that every other month is in Denver, and so I've been going to that and hanging out with the rest of them, and I now have a shared vocabulary that I can actually use with them, as opposed to before I started the book when I just sort of sat in the back and kind of sort of understood what they were talking about, but not really. Of course, like one of the reasons I'm really slow with this book is because I keep on going on tangents. I see something, and instead of just reading it and just like accepting it, I decide I want to program with it, play around with it a little bit, and that of course slows me down a lot. But I also feel that it increases my sort of my bounding knowledge about everything. I've looked into meetups in your area, but none popped up yet. You might always be able to create a meetup. There might be some other developers out there who are into Rust. My suggestion, since meetups are really expensive, is see if you're working for a company, they might be willing to sponsor you and like pay for the meetup fees. That's actually what I've done in the past. Using trait objects that allow for values of different types. In Chapter 8, we mentioned that one limitation of vectors is that they can store elements of only one type. We created a workaround in listing 810 where we defined a spreadsheet cell enum that had variants to old integers, floats, and text. This meant we can store different types of data in each cell and still have a vector that represented a row of cells. This is a perfectly good solution when our interchangeable items are a fixed set of types that we know when our code is compiled. However, sometimes we want our library user to be able to extend this set of types that are valid in a particular situation. To show how we might achieve this, we'll create an example graphical user interface GUI tool that iterates through a list of items, calling a draw method on each one to draw it to the screen, a common technique for GUI tools. We'll create a library crate called GUI that contains the structure of a GUI library. This crate might include some types for people to use, such as button or text field. In addition, GUI users will want to create their own types that can be drawn. For instance, one programmer might add an image and another might add a SelectBox. We won't implement a fully fledged GUI library for this example, but we'll show how the pieces would fit together. At the time of writing the library, we can't know and define all the types other programmers might want to create, but we do know that GUI needs to keep track of many values of different types, and it needs to call a draw method on each of these different typed values. It doesn't need to know exactly what will happen when we call draw method, just that the value will have that method available for us to call. To do this in a language with inheritance, we might define a class named component that has a method named draw on it. The other classes, such as button, image, and SelectBox, would inherit from component, and thus inherit the draw method. They could each override the draw method to define their custom behavior, but the framework could treat all of the types as if they were component instances and call draw on them. But because Rust doesn't have inheritance, we need another way to structure the GUI library to allow users to extend it with new types. Defining a trait for common behavior. To implement the behavior we want GUI to have, we'll define a trait named draw that will have one method named draw. Then we can define a vector that takes a trait object. A trait object points to an instance of a type that implements the trait we specify. We create a trait object by specifying some sort of pointer, such as the ampersand reference, or a box T smart pointer, and then specifying the relevant trait. We'll talk about the reason trait objects must use a pointer in Chapter 19 in the section Dynamically Sized Types and Sized. We can use trait object in place of a generic or concrete type. Wherever we use a trait object, Rust type system will ensure at compile time that any value used in the context will implement the traits object's trait. Consequently, we don't need to know all the possible types at compile time. So I believe this is where we had said, like, okay, trait blah, it will have the following function that will take in this and return this. But the implementation of that wasn't there. It was just, and it reminds me of in C, where at the top of the file you have basically your what is it? Your template functions. Is that? I feel like that's not the right word. But like the definition of the functions that are defining, like, hey, this is the function, this is the type it is, and this is what it's going to return. This is what it's going to take in. That's all one line. Then you go to the bottom of the file and you implement those functions so that they're available for everything else. This like traits sort of remind me of that. We've mentioned that in Rust, we refrain from calling structs and enums objects to distinguish them from other languages' objects. In a struct or enum, the data of the struct fields and the behaviors and implement blocks are separated. Whereas in other languages, the data and behavior combined into one concept is often labeled an object. However, trait objects are more like objects in other languages in the sense that they combine data and behavior. But trait objects differ from traditional objects in that we can't add data to a trait object. Trait objects aren't as generically useful as objects in other languages. Their specified purpose is to allow abstraction across common behavior. Listing 17.3 shows how to define a trait named draw with one method named draw. So public trait, and so this is exactly what I was saying. This is, we have the trait draw, and it's saying, well, anything that implements draw must have this function added to it. And I mean, it's an interface. This syntax should look familiar from our discussion on how to define traits in chapter 10. Next comes some new syntax. Listing 17.4 defines a struct named screen that holds a vector named components. This vector is of type box draw, which is a trait object. It's a stand-in for any type inside a box that implements the draw trait. So public struct screen, public components, vector box draw. So it's a vector that is going to contain boxes that each contain trait draw. Interesting. On the screen struct, we'll define a method named run that will then call the draw method on each of its components, as shown in listing 17.5. So implement for screen, have run, for component and self components, iterate components.draw. So yeah, we don't need to worry about the box anymore. It just, we iterate through the components. Well, I guess that dereferences the box automatically, which then gives us the thing. So that works there. I was watching a video with Brian Kernighan where he says, Rust doesn't feel like Rust tries to change C more than it should for him. But personally, he would still rather just use C. I've heard that from other people, but for other languages, like for example, Node.js, JavaScript on the server side, and or even like Python, Ruby, and the statement goes along with, well, I keep on finding I need to be really fast, so I write these components in C and then call them from these other languages, and I was doing it enough that I just gave up and now write everything in C. And I think it's an interesting statement because I'm not completely sure I agree with the speed these days. Like so many of these languages have optimized to the point where they're really, really fast. Like Node.js, it's doing some crazy compile time stuff to make it pretty close to C++ speeds. Written optimally in that language, but still pretty crazy. This works differently than defining a struct that uses a generic type parameter with trait bounds. A generic type parameter can only be substituted with one concrete type at a time, whereas trait objects allow for multiple concrete types to fill in for the trait object at runtime. For example, we could have defined the screen struct using a generic type and a trait bound as in listing 17.6. So public struct screen t. Well, so interesting, like this is not a generic. And this is. Public struct screen t, draw public components, a vec that takes in the type, implements type screen type, where t includes draw, public function run, and then just does the same thing. This restricts us to a screen instance that has a list of components of all of type button or all of type text field. You only ever have the homogeneous collections. Using generics and trait bounds is preferable because the definitions will be monomorphized at compile time to use the concrete types. On the other hand, with the method using trait objects, one screen instance can hold a vec that contains a box button as well as a box text field. Let's look at how this works, and then we'll talk about the runtime performance implications. I guess like what they're mentioning here is that you can use box to sort of hold different types. And we don't then have to create different structure, like implement different, implements, they're all wrong. That's an object-oriented term. We don't have to create a instance of the structure in order to like, for each type, it's gonna be the same type every single time. Now we'll add some types that implement the draw trait. We'll provide the button type. Again, actually implementing a GUI library is beyond the scope of this book, so the draw method won't have any useful implementation in its body. To imagine what the implementation might look like, a button struct might have fields for width, height, and label, as shown in listing 17.7. So struct button, so width, height, and label, and then implement draw for button, and then that actual code. The width, height, and label fields in button will differ from the fields on other components, such as a text field type that might have those fields plus a placeholder field instead. Each of the types we want to draw on a screen will implement the draw trait, but we'll use different code in the draw method to define how to draw that particular type. As button has here, without the actual GUI code, which is beyond the scope of this chapter, the button type, for instance, might have an additional implement block containing methods related to what happens when a user clicks the button. These kind of methods won't apply to types like text field. If someone using our library decides to implement a SelectBox, a struct that has width, height, and options fields, they implement the draw trait on the SelectBox type as well, as shown in listing 17.8. So use GUI draw, extern create GUI, struct SelectBox, with height and options, implement draw for SelectBox. So this is adding the trait in, and then coding the draw. Our library's users can now write their main function to create a screen instance. To the screen instance, they can add a select box and a button by putting each in a box T to become a trait object. They can then call the run method on a screen instance, which will call draw on each of the components. Listing 17.9 shows this implementation. So in main, we bring in the screen and a button, so that screen equals screen component. So we just set up. So we met, and this is where we're manually saying like, okay, we're using the boxes right here to hold these things. And this is nice because like the vector allows us to have these two different types in there. We didn't have to say, okay, the screen has to, like, we have one screen for a select box and one screen for a button. When we wrote the library, we didn't know that someone might add the SelectBox type, but our screen implementation was able to operate on a new type and draw it because SelectBox implements the draw type, which means it implements the draw method. This concept of being concerned only with the messages a value responds to, rather than a value's concrete type, is similar to the concept duck typing in dynamically typed languages. If it walks like a duck and quacks like a duck, then it must be a duck. In the implementation of run on screen in listing 17.5, run doesn't need to know what the concrete type of each component is. It doesn't check whether a component is an instance of a button or a select box. It just calls the draw method on the component. By specifying box draw as the type of the values in the component's vector, we've defined screen to need values that we can call the draw methods on. The advantage of using trait objects and Rust type system to write code similar to code that used a lot of codes. So type system to write code similar to code using duck typing is that we've never had to check whether a value implements a particular method at runtime or worry about getting errors if a value doesn't implement a method, but we call it anyway. Rust won't compile our code if the values don't implement the traits that the trait objects need. For example, listing 17.10 shows what happens if we try to create a screen with a string as a component. So string box, well, so we're still putting box new string from high. What we get, okay, because the string doesn't implement the draw trait. But if we added string, if we added a box trait to the string, then it would be fine, or the draw trait. This error lets us know that either we're passing something to screen we didn't mean to pass, and we should pass a different type, or we should implement draw on strings so that screen is able to call draw on it. Trait objects perform dynamic dispatch. Recall in the performance of code using generics section in chapter 10, our discussion on the monomorphization process performed by the compiler when we use trait bounds on generics. Compiler generates non-generic implementations of functions and methods for each concrete type that we use in place of a generic type parameter. The code that results from monomorphization is doing static dispatch, which is when the compiler knows what method you're calling at compile time. This is opposed to dynamic dispatch, which is when the compiler can't tell at compile time which method you're calling. In dynamic dispatch cases, the compiler emits code that at runtime will figure out which method to call. When we use trait objects, Rust must use dynamic dispatch. The compiler doesn't know all the types that might be used with the code that is using trait objects, so it doesn't know which method implements and which type to call. Instead, at runtime, Rust uses the pointers inside the trait object to know which method to call. There's a runtime cost when this lookup happens that doesn't occur with static dispatch. Dynamic dispatch also prevents the compiler from choosing to inline a method's code, which in turn prevents some optimizations. However, we did get extra flexibility in the code that we wrote in listing 17.5, and we're able to support in listing 17.9, so it's a trade-off to consider. I think Java implements this as well. Is it method overloading? I think it's method overloading, where basically you can manually create these generic functions where you say like, okay, here's the constructor and it takes these types. But then here's another constructor and it takes in these completely different types. And when you call it, depending upon what you pass in and how much how many arguments you pass in, it'll call the appropriate method for you. whenever you need to use it. So I guess you kind of like get those generic abilities, you just have to write them in manually. Object safety is required for trait objects. You can only make object-safe traits into trait objects. Some complex rules govern all the properties that make a trait object safe, but in practice, only 2 rules are relevant. A trait is object safe if all the methods defined in the trait have the following properties. The return type isn't self. There are no generic type parameters. Okay, so it's object safe. Methods defined in the trait have the following properties. So I guess like sometimes all the methods, well, does that mean, I guess a new wouldn't be that because it returns the full type, so it's not returning type self. There are no generic type parameters. That's interesting too. So we can't use generics then to call it object safe. The self keyword is an alias for the type we're implementing the traits or methods on. Trait objects must be object safe because once you've used a trait object, Rust no longer knows the concrete type that's implementing that trait. If a trait method returns the concrete self type, but a trait object forgets the exact type that self is, there is no way the method can use the original concrete type. The same is true of generic type parameters that are filled in with concrete type parameters when the trait is used. The concrete types become part of the type that implements the trait. When the type is forgotten through the use of a trait object, there is no way to know what types to fill in the generic type parameters with. An example of a trait whose methods are not object safe is the standard library's clone trait. The signature for clone method in the clone trait looks like this. So pub trait clone, function clone, takes and references self, and then returns self, a new copy of self. So that's and I think that's the reason why this is not object safe. The string type implements the clone trait, and when we call the clone method on an instance of string, we get back an instance of string. Similarly, if we call clone on an instance of vec, we get back an instance of vec. The signature of clone needs to know what type will stand in for self, because that's the return type. The compiler will indicate when you're trying to do something that violates the rules of object safety in regard to trait objects. For example, let's say we try to implement the screen struct in listing 17.4 to hold types that implement the clone trait instead of the draw trait. This. So public struct string, pub components are vector that holds boxes that implement the clone trait. They're then taken things that implement the clone trait. We would get this error. The trait standard clone clone cannot be made into an object. The trait standard clone clone cannot be made into an object. Trait cannot require that self-sized. This error means that you cannot use this trait as a trait object in this way. If you're interested in more details on object safety, then we can take a look at this RFC. Implementing an object-oriented design pattern. The state pattern is an object-oriented design pattern. The crux of the pattern is that a value has some internal state, which is represented by a set of state objects, and the value's behavior changes based on the internal state. The state objects share functionality. In Rust, of course, we use structs and traits rather than objects and inheritance. Each state object is responsible for its own behavior and for governing when it should change into another state. The value that holds a state object knows nothing about the different behavior of the states or when to transition between states. Using the state pattern means when the business requirements of the program change, We won't need to change the code of the value holding the state or the code that uses the value. We'll only need to update the code inside one of the state objects to change its rules or perhaps add more state objects. Let's look at an example of the state design pattern and how to use it in Rust. We'll implement a blog post workflow in an incremental way. The blog's final functionality will look like this. A blog post starts as an empty draft. When the draft is done, a review of the post is requested. When the post is approved, it gets published. Only published blog articles return content to print, so unapproved posts can't accidentally be published. Any other changes attempted on a post should have no effect. For example, if we try to approve a draft blog post before we've requested a review, the post should remain an unpublished draft. Listing 1711 shows this workflow in code form. This is an example usage of the API we'll implement in a library crate named blog. This won't compile yet because we haven't implemented the blog crate yet. So are we actually going to implement it for real? I kind of wonder if we're going to implement for real, I might want to actually do this one. The other one, they clearly said yeah, this is not going to really work. Extern create blog, use blog post. So in our main function, let mute post equals post new. Post add the text. Okay, so here's our wonderful blog. And then assert equal. Absolutely nothing is in the post content. Post request review. Assert equal nothing is in the post content. And then post approve. Assert equal I ate salad for lunch today is now what comes out of the post content. We want to allow the user to create a new draft blog post with the post new. Then we want to allow text to be added to the blog post while it's in the draft state. If we try to get the post content immediately before approval, nothing should happen because the post is still a draft. We've added assert equal in the code for demonstration purposes. An excellent unit test for this would be to assert that a draft post, blog post returns an empty string from the content method, but we're not going to write tests for this example. I'm pretty sure you make a blog when they teach you make your own HTTP crate. Oh, okay. Well, then in that case, I'm gonna wait and do it then. Next, we want to enable a request for a review of the post, and we want content to return an empty string while waiting for the review. When the post receives approval, it should get published, meaning the text of the post will be returned when content is called. Notice that the only type we're interacting with from the crate is the post type. The type will use the state pattern and will hold a value that will be one of the 3 state objects representing the various states a post can be in: draft, waiting for review, or published. Changing from one state to another will be managed internally within the post type. The states change in response to the methods called by our library's users on the post instance, but they don't have to manage the state changes directly. Also, users can't make a mistake with the states, like publishing a post before it's reviewed. This is basically a pretty standard state machine that is being built here. Defining post and creating a new instance in the draft state. Let's get started on the implementation of the library. We know we need a public post struct that holds some content. So we'll start with a definition of the struct and an associated public new function to create an instance of post, as shown in listing 1712. We'll also make a private state trait. Then post will hold a trait object of box state inside an option in a private field named state. You'll see why the option is necessary in a bit. So public struct post state, which is an option, box state, capital S state. Is there another Is there another structure state? Is that what he's saying? Inside an option in a private field name state, you'll see, okay. Content string, implement post, post state, some box new draft, then content string new, okay. Then we have trait, trait state. So we're using the same pattern we say last time, which this is a trait, a box trait. Is that what we called it? I already forgot the exact words they used. The state trait defines the behavior shared by different post states, and the draft, pending review, and published states will all implement the state trait. For now, the trait doesn't have any methods, and we'll start by defining just the draft state, because that is the state we want a post to start in. When we create a new post, we set its state field to a sum value that holds a box. This box points to a new instance of the draft struct. This ensures whenever we create a new instance of post, it will start out as a draft. Because the state field of post is private, there is no way to create a post in any other state. In the post new function, we set the content field to a new empty string. Storing the text of the post content. Listing 1711 showed that we want to be able to create a method called add text and pass it a reference to stir that is then added to the text content of the blog post. We implement this as a method rather than exposing the content field as pub. This means we can implement a method later that will control how the content field's data is read. The add text method is pretty straightforward, so let's add the implementation in listing 1713 to the implement post block. So implement post, add text, immutable reference to self, takes the test, and then we're going to push string in. The add text method takes immutable reference to self because we're changing a post instance that we're calling add text on. We then call push stir on the string in content and pass the text argument to add to the saved content. This behavior doesn't depend on the state the post is in. It's not part of the state pattern. The add text method doesn't interact with the state field at all, but it is part of the behavior we want to support. Ensuring the content of a draft post is empty. Even after we've called add text and added some content to our post, we will still want the content method to return an empty string slice because the post is still in a draft state, as shown in line 8 of listing 1711. For now, let's implement the content method with the simplest thing that will fulfill this requirement, always returning an empty string slice. We'll change this later once we implement the ability to change a post state so it can be published. So far, post can only be in a draft state, so the post content should always be empty. Listing 1714 shows this placeholder implementation. So implement post, public function content, it just returns a reference to the stir. And in this case is just returning an empty string. With this added content method, everything in listing 1711 up to line 8 works as intended. Requesting a review of the post changes state. There is a ton more in this one. Let's go through until 7:55 and then we'll call it a morning. All right, ensuring the content of a draft post is empty. Even after we've called add text and added some content to our post, we still want the content method to return an empty string slice because the post is still in a draft state, as shown on line 8 of listing 1711. For now, let's implement the content method with the simplest thing that will fulfill this requirement, always returning an empty string slice. We'll change this later once we implement the ability to change a post state so it can be published. So far, posts can only be in the draft state, so the post content should always be empty. Listing 1714 shows this placeholder implementation. So it's exactly the same thing as the other ones. Did I just go back too far and read the same one again? I may have. Requesting review of the post changes its state. Next, we need to add functionality to request a review of the post, which should change its state from draft to pending review. Listing 1715 shows this code. So we implement post, request review, mutable self. So we do an if let sum, or if, is it called if let? We take an option or a sum string, set that equal to self state take. This always, like, is that supposed to be in single equals or a double equals? Because that looks weird right there. It looks like I'm assigning this in this way, which might be what it is. If let sum s, and I haven't used if let before. I just read about it in a few different places, so I would need to play around with it a little bit more. Then we say self.state equals sum s, which is right here, dot request review. Trait say, then we request the review. So there's a setting up the trait. So our function, like, sort of definition here. Struct draft. Implement state for draft. Function request review. This is going to create a new box, new pending review. Struct pending review, implement state for pending review, function request review. Okay, goes on for that. I stopped at the if let chapter yesterday. It's my next chapter today. Awesome. We give post a public method named request review that will take a mutable reference to self. Then we call an internal request review method on the current state of post. And this second request review method consumes the current state and returns a new state. We've added the request review method to the state trait. All types that implement the trait will now need to implement the request review method. Note that rather than having self reference to self or reference to mutable self as the first parameter of the method, we have self, which is a type box self. This syntax means the method is only valid when called on a box holding the type. The syntax takes ownership of box self, and invalidating the old state, so the state value of the post can transform into the new state. To consume the old state, the request review method needs to take ownership of the state value. This is where the option in the state field post comes in. We call the take method to take the sum value out of the state field and leave a none in its place, because Rust doesn't let us have unpopulated fields in structs. This lets us move the state value out of post rather than borrowing it. Then we'll set the post state value to the result of this operation. We need to set state to none temporarily rather than setting it directly with code like self.state equals self.state request review. To get ownership of the state value, this ensures post can't use the old state value after we've transformed it into a new state. The request review method on draft needs to return a new boxed instance of a new pending review struct, which represents the state when a post is waiting for a review. The pending review struct also implements the request review method, but doesn't do any transformations. Rather, it returns itself because when we request a review on a post already in a pending review state, it should stay in the pending review state. Now we can start seeing the advantages of the state pattern. The request review method on post is the same no matter its state value. Each state is responsible for its own rules. We'll leave the content method on post as is, returning an empty string slice. We can now have a post in the pending review state as well as in the draft state, but we want the same behavior in the pending review state. Listing 1711 now works up to line 11. So interesting. We're not quite, we're almost to the halfway point of this page in this chapter. But it's 7:57, so let's go ahead and update where we're at. And then we will then we'll be continuing tomorrow morning. So no code today. Today was a big reading chapter. That's sort of what I was told to expect with a lot of the chapters after 12, which is it gets more into theory and how things can be done potentially, but not necessarily like full code alongs. Currently here we are. So we're at adding improved method, and then in here we click on U. And back to long methods on there. Let's update this on GitHub. In the middle of the blog example for OOP, kind of. Putting a kind of in there because everything that it really mentioned was OOP is kind of implemented in Rust. Not blindly, so not like some languages, which is like, we're going to do the OOP patterns and like, that's it. We're just adding everything in, it's textbook OOP. It kind of feels to me like they took a lot of the paradigms of OOP, thought about it, and then implemented it, but in ways that made sense for the developers. So in this case, they said like, well, we want inheritance, but also inheritance is dangerous if done incorrectly. So how can we basically force it so that you can't accidentally use it wrong? And it feels to me that that might be what the trait system is. Then we have like the implementations and the other things and instances, and the terminologies get changed around. So it's really hard to say like, oh, it's object oriented, because those all relied upon a shared state, a shared set of vocabulary that we're not using in Rust. But it is 8 o'clock exactly. We've pushed up this code, so I am going to go get ready for the rest of my day. I hope that you all have a great rest of your day as well. OOP is such an outdated method of programming. I doubt we'll see a new language ever made with a true OOP style. I mean, maybe, but then again, like, functional programming is really old too, and we keep on inventing new things only to discover that they were invented in the 60s. And so therefore everything is really old. So I'm not really sure, like, maybe eventually we'll like start out like forging on new things again with computer science. But maybe not. Maybe we'll just combine them together and do functional object-oriented programming, which is kind of how I see JavaScript as in a way. But with that, I'll be back tomorrow morning at 7 a.m. Mountain Time, where we'll continue on with this chapter, and we'll see how far we can get this week. Hope you have a great rest of your day, and I'll see you tomorrow.